all the time. And, his work on state models had a huge influence in the development of categorification and knot homologies. But maybe on a more personal level, I think, the thing that I learned most from Lou's work is that sometimes a picture is worth 1,000 equations. And that, it's really possible to do good and interesting mathematics by drawing lots of little pictures. And that's something I like to do and something, I'll try and emphasize today. Um, so thanks, Lou. Okay. Um, so let me go ahead and try and explain what I want to talk about. And so, the the other two words in my title, curves in the Fukaya category are maybe kind of scary, but satellites are something that I think most people who are interested in knots are familiar with. Okay, so when we think about satellites, okay, so what we have is we've got a pattern knot, which we'll think about as being, say, P inside of the solid torus, S1 times D2. And then we have a companion knot, C, sitting inside of S3. Okay, so here in the picture that I've drawn, we've got the two-strand cabling pattern in the trefoil knot. Okay, and we take a tubular neighborhood of the companion knot to form the satellite. And the satellite, SP of C, I'll call it, is the image of P under this tubular neighborhood, phi. Okay, so here's the two-strand cable of the trefoil. Okay, and now a very old theorem about satellite knots is the fact that they're very well behaved with respect to the Alexander polynomial. Again, hopefully the Alexander polynomial's, something that most people who are interested in knot theory can get on board with. Um, so we have this formula that says that the Alexander polynomial of the satellite is the Alexander polynomial of the companion, but evaluated at t to the w, where w is the winding number of the pattern. So here for this cabling pattern, that would be 2, times the Alexander polynomial of the pattern. Okay. And so in this example here, the Alexander polynomial of the trefoil is t minus 1 plus t inverse. So here I get t squared minus 1 plus t to the minus 2. Winding number is 2. And this pattern sitting inside of S3 just gives me the unknot. So here I get 1. Okay. And as I was preparing this talk, I realized that I didn't actually know who first proved this formula. Satellite knots weren't invented until about 1949, so my guess is it must be kind of in the Fox era of the Alexander polynomial. But if anybody knows, do tell me in the questions. Okay. All right, so now the next thing maybe I want to talk about a little bit is the notion of knot-Floor homology, which is kind of a categorification of the Alexander polynomial. Okay. And this theory comes out of the Heegard-Floor homology of Ostwald and Szabo. That's where it comes from. And so maybe just to consider a simple case, if I have a knot K in S3, its knot-Floor homology in the simplest formulation is just a bunch of bigraded groups. Okay, so here I'll grade them by J, which is the Alexander grading, corresponds to the powers of T in the Alexander polynomial. Okay, and so what's the precise relation? So if I take the graded Euler characteristic of the knot-Floor homology, so in other words, if I take the Euler characteristic of each of these summands HFK hat of K comma J and form a generating function, then of those Euler characteristics, then I get the Alexander polynomial. Okay. And in honor of Lou, let me mention a theorem of Ostwald and Szabo, proved using the Kaufman state model, that says that if K is alternating, then actually there's not too much more information in these groups than there was in the Alexander polynomial itself. Okay, so the dimension of this group HFK hat of KJ is the sort of minimum that it could be given this relation. Okay, and you can say more than that, but let's just say it that way. Okay. All right, and so a really interesting question um, that you can ask is, well, there's this nice formula for the Alexander polynomial of a satellite knot. What can you say about the knot-Floer homology of a satellite knot? Um, is there any analog of this formula? Okay. This turns out to be a really complicated and interesting question. And it's maybe no accident that both Ojvath and Szabo's first students who graduated working on Heegard-Floer homology actually studied this question. This is a long line of interesting work, starting with the work of Eftekari and Hedden, proceeding through Hom and Levine and Petkova, Hanselman Watson, Chen, Guth, Kang, and I'm sorry if I've omitted you, because there's, really just a lot of incredible work in this area. And as you can see from, all the people who've written about it, the answer isn't just as simple as this formula. Okay, but that's a good thing. Okay, it turns out that taking satellites is a really good way of constructing knots with interesting and complicated knot-Floer homology. And that turns out to be good for lots of different applications. So these satellites have been very useful in many applications. Okay. So now let's come to the curves bit in the title of the talk. Okay. And maybe if you know the Alexander polynomial a little bit, you'll really know that the Alexander polynomial is an invariant of the complement of the knot. Even it's an invariant of the fundamental group of the complement of the knot. Okay, so you could ask the same question about the knot-Floer homology. So is the knot-Floer homology an invariant of the complement of the knot? And it turns out that the answer is no. Okay, so really the knot-Floer homology is an invariant of the knot sitting inside the manifold that it sits in. All right, and to specify that manifold that sits in terms of the knot complement, one thing I could do is I could take the knot complement EK and look at its meridian. Right? If I know the data of the knot complement and the meridian, then I have the knot sitting inside the manifold. Okay, and so one way we could think about that is actually there's this thing called the sutured manifold, okay, which basically corresponds to coloring the boundary of the knot complement red and blue. Okay, as I've shown in this picture, there's the boundary torus. And the dividing curve between red and blue is parallel to the meridian. Okay. And so actually the knot-Floer homology is a special case of this sutured Floer homology. Okay. All right, so a very natural question to ask is, can we find a Floer homological invariant? Kind of like the knot-Floer homology, but that's genuinely an invariant of EK, of the exterior, and not of the knot inside the manifold. How should we think about that? What's the Floer homology of the knot complement? And so it turns out that the right way to think about this question is via the bordered sutured Floer homology of Rumen-Zarev, which itself sort of is an extension of the bordered Floer homology of Lipschitz, Ojvath, Thurston. Okay, that's maybe a scary sounding set of words. But this bordered sutured Floer homology at the level we're going to talk about it is maybe not so complicated to think about. So what am I allowed to do? I'm allowed to take the boundary of my manifold and I color part of it. So here I took the exterior of the knot complement and I colored a little bit of it with this red and blue disc. So I didn't have to color the whole boundary like I did for this sutured manifold. I left some of the boundary uncolored. That's called the bordered part, this white part. Okay. All right. And so the slogan here is that M twiddle is a balanced bordered sutured three manifold, a little bit of a mouthful, whose bordered boundary, that's like the white part here, is the punctured torus. Okay, and I have to think about the coloring on the boundary of the white part, right? So here in this boundary of the white part, I've got one blue arc and one red arc. Okay, so if the bordered boundary looks like that, then the Haggard-Floer homology of that object is actually an object of the Fukaya category of that punctured torus, um, stopped along the blue part. Okay. Now, of course, I have to tell you a little bit about what does it mean to be an object of the Fukaya category of the punctured torus. That sounds scary still. But maybe let's just, before we say a word about that, let's notice that anytime I have a knot complement, I can do this thing where I take the knot complement and I slap down this little kind of yin-yang symbol, blue and red, on the boundary. And that's a little bit of data. I picked a point, or maybe a neighborhood of a point, on the boundary of the knot complement, but it's not so violent as picking a meridian like we did up here. Okay. But I can do this thing, in many other circumstances. So for example, if I had a manifold with two torus boundary components, like a link complement, well, I could suture one boundary component, color it all red and blue, and put a little disk yin-yang on the other one, right? That's a situation to which this slogan applies as well. Okay. So this situation is more general than just what happens for knot complements. Okay, so now let's say a little bit about the Fukaya category. Okay, and the good news about the Fukaya category is that in the case that we're interested in, we're looking at the Fukaya category of this punctured torus, we can understand that by drawing little pictures. Okay, and really, maybe I should say that we're going to take a covering space of this punctured torus, but that's still something I can draw a picture of. Okay, the objects of this Fukaya category, that's maybe a scary sounding phrase, but really they're just direct sums of immersed arcs. Okay, that's something we can draw on a piece of paper, ending on the red part of the boundary here, and immersed loops. So, arcs that close up to form loops. Okay, and so that's something we can really draw pictures of and think about in a concrete way. Okay, so maybe just to describe a few examples of this process. So I could take the unknot complement, which is the solid torus, okay, and put this yin-yang on it. And when I do that, I'm supposed to get an object in the Fukaya category of a covering space of the punctured torus. Okay, so actually the covering space is kind of completely determined by homological data. Okay, how H1 of the boundary includes into H1 of the three manifold. Okay, and in this case, the covering space, I've drawn a bit of it here, is this infinite punctured flute. Okay, so there are a bunch of holes that are kind of, lifts of the puncture. And the curve that I get in this case is just this circle that wraps once around the cylinder, okay, between two of the punctures. So that's, simple manifold and a simple curve. Okay, if I had something a little bit more complicated, like the exterior of the trefoil, then I'd get a curve that was a little bit more complicated. Actually, it looks like this. Okay, you'll notice that it's still a closed curve. Okay, actually, if I take the exterior of any knot complement and do this, then we'll get a union of closed immersed curves. Okay. Maybe let's look at a couple other examples that don't come from knot complements. So the first example I want to talk about takes place where the underlying three manifold is T2 times I, so the thickened torus. So we're back in this situation here, where we've got two boundary components, and we're going to suture one completely. Okay. But actually, what I'm going to take it back, right? So it's really T2 minus D2 times I. So what I really want to do in this picture is I want to drill a hole out of the torus, so a tunnel between the top and the bottom boundaries. Okay. And now the top boundary here looks like a torus, and I'm going to color it red and blue just like this. Okay. You can see. And then I'll just continue that pattern of coloration down to the bottom of the tube. Okay, and then on the other side, down here, I've got a bordered boundary that's a once punctured torus. So we're in the situation that we can talk about here and draw pictures of. Okay, and it turns out that the invariant for this manifold is really just a line segment between two of these punctures. So now actually the covering space that we're thinking about is the kind of universal abelian cover of the punctured torus. So we get R2 minus a lattice of puncture points. A picture that's almost the same, but a little bit different, is here if I really took T2 times I, so this should belong down here. Okay, I could color the top the same way I did before, but not drill out the hole. And instead just put this little yin-yang down here. Okay. And when I do that, I get a picture that, well, looks like maybe it's got something to do with this, but it's not quite the same. I got a little figure 8 going around these two punctures. Okay. And again, that's not an accident. The fact that sort of I just have this yin-yang boundary on this side means that I get a compact object in the Fukaya category, a union of loops. Okay, whereas kind of here I had this tunnel, and that results in a non-compact object. Okay. So now we could kind of rephrase our question about the knot-floor homology in terms of these curve invariants. Okay, and I'd like to argue that's a good thing to do because that makes this question kind of functorial in a way that I'm going to explain in a minute or two. Okay, so we could ask, what's this curve invariant, HF hat, of the exterior of the satellite knot, where maybe I just put a little yin-yang on the boundary? Okay, and how's it related to the curve invariant of the exterior of the companion? Okay, so like I said, this is a good thing to do because we can think about it in a sort of functorial way. So we can think about the pattern knot determines a sort of bordered sutured cobordism. Okay, between the once punctured torus and itself. Okay, and that ought to induce a functor. Let me call it FP hat. From the Fukaya category of the punctured torus to the Fukaya category of the punctured torus. Okay, scary sounding words again, but all this says is that I have some function that eats immersed curves in the punctured torus and spits out, those are combinatorial objects, and spits out other immersed curves. Right? So the kind of the target and the domain are both have nice combinatorial descriptions. So we can hope that maybe there's a combinatorial way that we can think about this functor. Okay. And so then the answer to the question up here is that kind of the curve invariant for the satellite will be the image of the curve invariant for the companion under the action of this functor. Okay, so to understand the satellite operator for a particular pattern, what we need to do is we need to understand what this functor from the Fukaya category of the punctured torus to itself is. Okay. Well, how could we hope to do that? So maybe one thing we could do is we could dualize the problem a little bit. Instead of thinking about this functor this way, we could think that actually maybe both boundary components of my pattern P are kind of on the that end, the end of the functor. Okay, I've got a cobordism from the empty set to two copies of the punctured torus. Okay. And then the general yoga of how this theory works will tell you that then I should get an invariant that's in the Fukaya category of the product of the punctured torus with itself. Okay. Um, Maybe that sounds scary. That is scary, actually. That's much scarier. But in the best possible case that we could hope for, um, this object here is maybe really induced by a Lagrangian surface, a geometric surface inside of this product. Okay. And this functor is just push-pull. So I have two projection maps from the product to either factor. I can push the Lagrangian down one way, I can push the Lagrangian down the other way. And what does this FP hat do to curves? Well, I have some curve down here. I take its preimage up here, and then I push it forward. Okay, so in the best of all possible worlds, that would be how we could describe this functor. Okay, so there are some pretty obvious problems here. Okay, so maybe the first problem is that in the kind of curve case, we had this very powerful structure theorem, okay, that told us what the objects of the Fukaya category were and that they were actual nice geometric things that we could draw. Okay, there's no structure theorem for the Fukaya category of this product of two punctured tori. We expect that, the generic object there looks like kind of an iterated mapping cone of geometric Lagrangians. Pretty bad. Okay, so that's a problem. I mean, maybe, a less serious, but still, an issue is that it's harder to draw pictures of a Lagrangian surface inside a four manifold. Right? So if you'd like to draw little pictures, maybe that seems more difficult to think about. Okay. So I don't have true solutions to either of these problems, but let me just say, what kind of solutions can I offer to them? Well, I think that the solution I have to offer for number one is hope. Okay. Doesn't sound so great, right? But we can hope that in the examples we care about, that P prime might actually come from a geometric Lagrangian, an actual surface embedded in the product of those two punctured tori. Okay. And for two, well, there's a pretty concrete answer that we could think about, which is that instead of trying to think about this four manifold in our heads, we should think about this abstract surface, P prime, and the maps that it has to, the two maps pi 1 and pi 2 that it has to the two factors. Right? And that's something that, we can think about in our heads in a geometric way and draw pictures of. It's a little harder than drawing curves, but, maps of surfaces is something that you can draw a picture of. Okay. And so I guess what I want to say in this talk is that, the evidence suggests that actually that this hope is not a completely unreasonable one. Okay. So we can describe this data in two for some simple but still pretty interesting examples. Okay, so that in some cases we can really say what this functor looks like by drawing pictures. Okay, so let me talk a little bit about the examples I want to consider. Okay, so maybe the first example I'll talk about is the cabling operator. So this was already described quite a while ago by Hanselman and Watson. I've just drawn the two-strand cabling operator here, but this works for arbitrary cables. Okay. And you'll notice that I put a little purple tail in here. Okay, so if you're a little bit familiar with bordered sutured floor homology, right? So this purple tail is indicating that I've actually drilled out that arc. Okay, and I've got a tube going there where it's sutured, you know, kind of the way that we had for the first example in T2 times I. So half of the cylinder is colored red and half of it is colored blue. Okay, so on the top boundary here, I've got one punctured torus, and on the inside boundary, I've got another. Okay. Um, Another example that sort of generalizes this particular one that I've drawn here is that I could think about the exterior of a two-bridge link, right? So this cabling pattern is the exterior of the two-bridge link 4-1 that looks like um, this. Okay. Um, this here is the two-bridge link 8/3, rational link 8/3, which corresponds to the Whitehead pattern, if you're familiar with that. Okay, and notice that again, for a two-bridge link, I have a natural kind of tunnel here that I'm going to drill out to get this operator. Another operator that we could consider is what's called the tube cutting operator. Okay, so this is a cobordism from the torus to itself, whose underlying space is just T2 times I. Okay, but instead of taking the identity cobordism, which would correspond to drilling this cylinder out, I've just put a little yin yang on both components. Okay. And that's another perfectly good bordered sutured cobordism. Interesting operator. Another operator that's nice to consider is the sort of add a strand operator. Okay, where what I do is, again, I take the identity cobordism for T2 times I, which is really punctured T2 times I. And then I drill out another strand parallel to the boundary. Okay, so that's a manifold with three bound. If I forget this tube for a second, that's a manifold with three boundary components. That's a little complicated to consider. So what I'll do is I'll suture this tube that I drilled out here, um, red and blue like this. Okay, so again, that's a legitimate thing that I can do. Okay. Um, okay. And so now what I'd like to do is I'd like to just draw a few pictures and talk about what are these, what are these operators in these cases? What are the surfaces and what are the maps? Okay. So let's start with the two-strand cable operator. Okay. And as many of you probably know, the exterior of this operator is ciphered fibered. Okay. Of course, it's the complement of a link in S3, so H1 of the complement is generated by meridians M1 and N2. And the fiber lives on the boundary. It's actually the class of 2M1 plus 2M2. Okay. And if I were to look at the homology of either boundary component, I'd find that it was generated by the fiber in the corresponding meridian. Okay. So that's just, little easy algebraic topology that sort of figures in this calculation in ways that I won't completely explain. Okay. But actually it turns out that this P prime here, okay, is just a 2-to-1 cover of the torus. Okay, so it's it is itself a torus, but now with two punctures. Okay, and it maps 2-to-1 to either of these two boundary components by a covering map. Okay. And since these are covering maps, I can sort of describe which 2-to-1 covering map it is by describing which subset of H1 of the boundary torus H1 of the cover is. Okay, and the answer is that there's a kind of obvious subset for this, which is I take the span of 2M1 and 2M2. Okay, that's an index 2 subgroup of both of these. Okay, and this is, this fact that we have a 2-to-1 cover is actually reflective of an important geometric fact that's going on here, which is that the kind of algebraic degree of these maps, in this case, maybe where we have a link complement, is given by looking at the homology of the link complement. And here it can be expressed just in terms of the linking numbers of the two components. Right? So a two-strand cable corresponds to the complement of a link, the easiest link with linking number 2. So the fact that this map is degree 2 isn't an accident. It's reflecting that linking number. Okay. So now let me draw a picture of kind of the actual how you should think about this map. So I think actually a good way to think about this map is to take, again, the universal abelian cover of the boundary torus. Okay, so the boundary torus here is a fundamental domain for the boundary torus looks like this. Okay, and I haven't chosen the standard meridian longitude basis for the homology of the boundary torus. Instead, I've chosen to cut it up along the meridian in the fiber. Okay, that's a natural choice because the fiber is such a natural piece of data on this Seifert fiber manifold. Okay, and so the fundamental domain for this 2-to-1 cover here, well, I could think about it as being these two squares here, mapping down to the quotient of this R2 by the obvious lattice that you see in the picture as shown. Okay. So that's a 2-to-1 cover. And so the map over here looks very similar, and that's not surprising because the two boundary components of this two-bridge link are symmetric. Okay, the map here actually it takes this A1 here to this square, but it bends this square over here like this. Okay, and so that's a very simple map that completely describes this operator on floor homology. Okay. And yeah, so I should say that, this case was originally described by Hanselman and Watson, not quite in this way. And more recently, Chen and Hanselman kind of given a generalization of this picture that applies to complements of one-bridge braids. Okay, and there for complements of one-bridge braids, again, you expect that you get covering maps here. Okay. So let's think about maybe now an operator that doesn't come from a covering map. Okay, and an interesting example here is this tube cutting operator. Okay. So for the tube cutting operator, the genus of this underlying surface is 2. Okay, and it's convenient to draw, again, the universal abelian cover of both boundaries. So we get this lattice inside the plane, and the corresponding covering space of this P prime, which looks like I take this 4-punctured sphere and I glue it together in the obvious lattice-shaped way. Okay. And the projection in one direction here is just this operator. Okay, so I hold it over there and I squash that surface flat. Okay. And again, this tube cutting operator is very symmetric. Okay, so the projection going the other way looks very similar, except before moving it over here and squashing this flat, um, what I do is I take the surface and I do a Dane twist along this purple curve, which if you think about it, this purple curve is really surrounding this puncture here. Okay. So if I think about what happens, maybe it's a good case to explain what the push-pull really looks like. So say, for example, that I had this red curve here running between two boundary components. Okay, that's a non-compact curve, but in this picture here, it would pull up to a compact curve that looks like this. Okay, and then when I do the Dane twist around this boundary, well, I guess I really did it around all of these boundaries here. What you'll see is that this red curve gets twisted around the punctures before I push down. And so the image when I push forward is exactly this figure eight. And if you think back to those two examples that I drew right here, okay, you'll see that this object is obtained by applying the tube, this object here is obtained by applying the tube cutting operator to this one. And that's, well, because if I glued the tube cutting operator onto this, I would have gotten this thing. Okay. So, all right. So now, just to illustrate some interesting things that can happen. Okay. Let's talk about the add a strand operator. Okay, so actually this add a strand operation figured prominently in Gorski-Ham's calculation of the knot floor homology of the link floor homology of the NN torus link. So it's interesting to compare, this kind of way of thinking about it with their calculation. So this add a strand operator, again, is represented by a surface of genus 1. Okay. And when I sort of pass to these covers, this surface of genus 1 uncovers to cylinder here. Okay. And very similar to what happened in the tube cutting operator, the map pi1 over to this cover of the punctured torus, what does it do? Well, it takes the cylinder, it takes the cylinder, moves it over here and squashes it flat. Okay, onto the plane. Okay, so these 2 points right here both squash flat onto this puncture. And this circle here squashes flat onto here. And this whole region here squashes flat onto here. Okay. Now, well, the other map here, again, this is a symmetric operator, but I've sort of chosen to write it nicely with respect to these coordinates. The other map here, what it does is it takes this annulus and wraps it around the cylinder kind of in this way. So this is kind of going around the back of the cylinder. Okay, and so again, for example, I could see that if I took the push-pull of this curve in the plane here, it would lift up to this red cylinder here and then wrap around and form this figure eight like this. Okay. And maybe I'm going to skip, there's a kind of detailed drawing of how this wrapping goes, but I think we'll skip it so we don't run over. Okay. And I have to say that for a long time, I thought that it was only possible, you know, to draw these pictures in the case maybe when the complement is Seifert fibered in some sense, like that tube cutting operator is again corresponds to a Seifert fibered manifold. But in fact, that's not the case. And it turns out that it's possible to, you know, to draw these operators for at least some two bridge links as well. So maybe let me just kind of quickly indicate what the operator for the Whitehead link looks like. Okay, so this is the operator that tells you how taking the Whitehead double acts on curves. Okay, and again, so the underlying surface corresponding to this operator has genus 1. We kind of unroll it to draw this picture in the plane. It unrolls to this infinite cylinder here. And you can see that if we take the kind of quotient by this action translating by this way, I get a genus 1 surface. Okay. And well, again, this is a two bridge links are symmetric. The image on the other side should look very similar. Okay. And it does. The image looks like this. But the map that applies to this, we have to sort of do a kind of non-trivial map to go from here to here. Okay, and that map takes this, maybe let me draw it in a different color, this purple region here, for example, and spreads it out kind of first on the front and then on the back of this image over here. Okay. Okay. So I'm almost out of time. So I'd like to kind of reprise and sort of say a few things about how things that we know about Knopfler homology kind of correspond to geometrical things in this picture over here. Okay, so for example, Knopfler homology tells you about the Alexander polynomial of the knot. All right. And so, when you're thinking about Floer homology, one of the first questions you should always ask yourself is about the Euler characteristic, in some sense. And so what that should be saying in this case is that what is the Euler characteristic ought by general yoga to be related to the multivariable Alexander polynomial. Okay, and actually here in this kind of push-pull picture, there's a very precise relationship with the multivariable Alexander polynomial. Namely, I have that puncture, okay, and I look at the pre-images of the puncture. Okay, and actually each of those pre-images comes with a sign, whether the map is kind of orientation preserving or reversing near the puncture. And it comes with some kind of a translation, which is how it maps, where they get mapped to under pi 2. Okay, and if you think about it, if you add up those signs and those translations, they're exactly giving you the multivariable Alexander polynomial. So like if we thought about the two-strand cable operator, okay, that was a degree 2 cover, 2 pre-images of the puncture, 2 terms in the multivariable Alexander polynomial. Okay. The fact that the Knopfler homology is visible in the Alexander polynomial for the torus knots, that's analogous to the fact described by Chen Hanselman that this map is a covering map. Okay, so if it's a covering map, then actually all of the pre-images of the puncture contribute with the same sign. Okay, And so there's kind of no cancellation in the Alexander polynomial. And moreover, every term in the Alexander polynomial has the same sign. So if you know the Alexander polynomials of these one-bridge braids, that's a kind of nice feature that they have, is that every term is positive. Okay. And the last thing that I want to say, so for alternating knots, right, again, this fact that the dimension of the knot floor homology is visible in the coefficients of the Alexander polynomial. Okay, and so what should be happening over here on this side? Well, maybe an analog of that statement, okay, is the conjecture that if, say, I give you a two-bridge link, okay, then, this P prime exists as a geometric surface. And actually, not the algebraic degree, that's given by the linking number, but the geometric degree of this map is exactly given by half the determinant of my two-bridge link. Okay, so I'm out of time, so I'll stop here.
Great. Thank you, Jake. That was great. Thank you very much. So now we would